My name is Isabella, and today I'm going to be presenting the assemblage assessment for island conservation in Indonesia. The plant assemblage assessed is composed by 15 species that present different ecological attributes, and I'm highlighting 3 endemic species, 11 native species, 1 non-native species, and 8 species that are considered in some threatened category. This table is summarizing all the relevant information about the species, and I have found highlighting these interesting species such as Amorphophallus gigas that it is only considered at the local level as an endangered species, and it is the tallest flower of the world. Another species is the Anophelis javanica, which is an endemic species as well, and it is only local considered as an endangered, and in an area of the country it's already driven extinct. This is why it's protected under the law. Another species that is vulnerable but considered as in the category as the international level red list is the Burbidia Schizocelia. Um, Also considered at the international level, in some threatened category, there are these 2 species belonging to the Curcuma genera that it also happens to be of economic importance for human communities. And finally, the species of Rafflesia arnoldi that is considered only at the local level as vulnerable and endangered, and it happens to be the largest flower of the world. To evaluate the diversity and assess the conservation decision, I have performed analysis related to alpha diversity, beta diversity, as well as analysis considering rarefaction, rank abundance curves, and species area relationship. I also did a design of decision-making matrix to rank islands based on their plant assemblage components and reduce bias in the final decision making. These two graphs are representing the relationship between sampling size and number of species, in which it is suggested there is a need of a major sampling effort, particularly for island 1, 3, and 2. This could also be related with the size of the island, in which a higher or a largest areas will need a major sampling effort that it's actually reflected in the small size of the island 5 and 4, that with this sampling effort that it was made, they reach so close their maximum of species richness. This analysis of species area relationship is showing that with the increase of area, there is an increase of species richness. However, once the islands are reaching around 60 kilometers square, the species are no longer added to these increasing areas. This could be suggesting environmental limitations, resource limitations, and biotic interactions such as competition. I could have also analyzed another diversity patterns such as intermediate disturbance hypothesis, latitudinal gradient biodiversity, and diversity productivity relationship. But in order to do this, we need data such as disturbance gradient, sampling at different latitudes, and also having data such as biomass per unit time, productivity rates, and other traits that can be related with productivity relationship. So far, we have considered only the size of the islands as the main drivers of these patterns of diversity and abundance. But we need to take into consideration that it could be environmental factors that are driven these differences of the patterns that we're seeing here. And for example, being big doesn't necessarily mean that habits are being more heterogeneous. And other anthropogenic activities could be happening in shaping distribution of a species or species occurrences in the islands. And finally, natural disturbance regimes also affect species distribution, and it is important to take into account these other factors. Following up with the explanatory analysis, I performed a rank abundance curves that are reflecting abundance patterns in which most species are rare, few are common. The curves are suggesting that island 1, 2, and 3 have a high diversity since the dominance is not prominent as it is for island 4 and 5. I could have done as well another analysis for species abundance patterns. For example, the niche centrality hypothesis and the widespread pattern. But in order to do this, we need data to analyze, or data that is reflecting a niche characterization, habitat suitability, ecological niche modeling could provide valuable results to make this analysis, and also like distribution, geographic range, and species overlapping. Alpha and beta diversity results are summarized in this table, and I found that island 1 has the highest values in the community components, followed by island 3 and 2. And this is shown in the different diversity index and components that I measure. And so we're seeing here that with 15 species, island 1 it has the richest it is the richest island that we can find here, followed by island 3 and 2. It is also following the same pattern for the abundance, for a total of 138 individuals. And when measuring the diversity indices, such as Simpson's and Shannon, which it happens to be also consistent within them, in which island 1 is highlighted as the most diverse island, followed by island 3 and 2. This is reflecting a high level of equitability or evenness, and later it is related with a low level of dominance in this island. And following up with the rank abundance curves, it is suggesting both indexes and curve analysis. The rank abundance curve analysis suggesting this pattern of low dominance for these islands. Regarding beta diversity, it is suggested that the species that are present in island 5 and 4 are going to be present in island 1, 2, and 3. Regarding the uniqueness of island, I decided to compare island 1 against the rest of the islands, since island 1 it has the highest level of diversity. And so island 5 and 1 are basically sharing almost 90% of the species, suggesting that island 1 is acting as a source, meaning that island 5 would be a sink, following the premise of island biogeography theory. And this is also happening for island 4, island 2, and island 3. However, island 3 has the lowest or the highest uniqueness, right? Because it's only sharing 24% of the species with island 1. However, I need to highlight also the importance of island 5 and 4, because based on their endemic proportions, they have the highest endemic proportions. And this could be, and also like species density. And this could be reflecting connectivity isolation, particularly for island 5. So, based on the diversity estimations, the implemented matrix show that Island 1, 3, and 2 have the highest potential to be conserved and protected. Therefore, with the available budget, Island 1, 2, and 3 are going to be conserved, and because they are not only maintaining diversity, but it's enhancing connectivity for future conservation strategies and implementations. However, it is important to consider that there were other factors that we didn't analyze here, and it could be as much as important of the indexes and all the analysis that I did, because for future implementations, there is a lack of clear analysis of connectivity and like what is the actually isolation within these islands. There is also a need for resource availability evaluation that could be reflecting the biotic interactions such as competition. And finally, we need to consider the humans factors, right? So the social consideration in which social economic activities shape the species communities and limit the conditions in which we could make conservation strategies or we can implement these strategies. And finally, we need to assess social conflicts that could potentially limit as well the implementations that we could be done in the future. Thank you for your attention.